Okay, so in this chapter, we're going back to linear regression, which is something we talked about, I believe it was chapter 3, where we found the predicted line. We were able to find the linear regression line and we could predict values of our variables. And now what we're going to be doing is taking inference about linear regression. So in this first part, when a scatter plot shows a linear relationship between the quantitative variable x and the quantitative response variable y, we use the least squares line fitted to the data to predict y, remember we called that y hat, for the given value of x. If the data are a random sample from a larger population, we need statistical inference to answer questions like these. So back when we did this before, we had a population. We're talking now that if we have a sample. So is there really a linear relationship between x and y in the population, or could the pattern we see in the scatter plot plausibly happen just by chance? In the population, how much will the predicted value of y change for each increase of 1 unit in x, which is really what's the margin of error for this estimate? Whoops. They vary quite a bit from the original population regression line, which was 10.36. Confidence intervals and significance tests about the slope of the population regression line are based on the sampling distribution of B, the slope of the sample regression line. So B is going to be our slope of our sample regression line. If you look at this, that red vertical line on this graph is 10.36. That is the population slope for our regression line. But if you look at this, so this is if we take every possible sample of size 20 and plot their slopes. Notice that the shape is roughly symmetric and unimodal. It kind of looks approximately normal. The center of the 1000 B values is 10.35, and this value is quite close to the slope of the population, 10.36. And the spread, the standard deviation of the whole sampling distribution is 1.29. Later we'll see that the sampling deviation of the sampling distribution of B is actually 1.27. So here are some of the things that we have to talk about, or that we have to check when we're using a sampling distribution of slope. So if we choose an SRS of n observations from a population of size n, with the least squares regression line, the predicted y hat, is equal to a, which is our y-intercept, plus beta times x. Let b be the slope of the sample regression line, so that was the population one, the y hat one. The mean of the sampling distribution of b, mu sub b, is actually equal to the slope, or beta. The standard deviation of the sampling distribution of b is sigma sub b, which is equal to the population standard deviation divided by sigma sub x times the square root of n. Again, as long as the 10% condition is satisfied. I think when we go over an example, this will make more sense to you. The sampling distribution of B will be approximately normal if the values of the response variable y follow a normal distribution for each value of the explanatory variable x, the normal condition. So for conditions for regression inference, the regression model requires that for each possible value of the explanatory variable x, the mean value of the response variable, mu sub y, falls on the population regression line, and the values of the response variable y follow a normal distribution with a common standard deviation of sigma. So for any fixed x, the responses y follow a normal distribution with a standard deviation of sigma. So if you look at this, I think it's a little crazy, and I'm hoping that once we get to the example, will clear it up. I'll try to maybe talk about this a little bit in class. So we're really to the conditions for regression inference. What do we have to check? So if we have n observations on an explanatory variable x and a response variable y, our goal is to study or predict the behavior of y for given values of x. We have an acronym that we can use called LINER. First, we have to check that it's linear. The actual relationship between x and y should be linear, so we'll make a scatter plot and look at the data. For any fixed value of x, the mean response mu sub y falls on the population true regression line, mu sub y equals alpha plus beta x. It has to be independent. Individual observations are independent of each other. When sampling without replacement, check the 10% condition. Has to be normal. For any fixed value of x, the response variable y varies according to the normal distribution. The standard deviation of y, or sigma, is the same for all values of x, so equal standard deviation, and it has to be random. The data come from a well-designed random sample or a randomized experiment. And notice that makes the acronym LINER. So how to check? Start by making a histogram or a normal probability plot of the residuals and also a residual plot. Examine the scatter plot to check that the overall pattern is roughly linear. Look for curved patterns in the residual plot. Check to see that the residual center on the residual equal to 0 line at each x value in the residual plot. Independent. Look at how the data were produced. Random sampling and random assignment help to ensure that the independence of individual observations. If sampling is done without replacement, check the 10% condition. Normal. Make a stem plot, histogram, or normal probability plot of the residuals and check for clear skewness or other major departures from normality. Look at the scatter plot of the residuals above and below the residual equal to 0 line. If the vertical spread of the residuals should be roughly the same from the smallest to the largest x value. And random. Make sure the data were produced by random sampling or in a randomized experiment. I think when you watch the next video, which goes through the example, it'll take all of this and make it clear for what we'll do tomorrow.